there's a lot of work that has taken place in the last 10 years on silver, and one of my postdocs was on Greek and Roman silver coinage, and that's where I got into lead isotopes and chemical analyses. But the work here, there's a lot of work by people like Stephen Merkel, who have analysed a lot of dirhams. So yes, you've got some of the different dirham types at the bottom, which are Umayyad, Aghlabid, Alex knows more about these, Mohalabid, and I've put on here a shatter from the north. That's just for later as a little point of reference for further work. And at the top, some of these lead seals with Kufic or Islamic inscriptions. What I want to do is kind of rush through background into lead isotope analyses. It's quite standard. If you know about it, I'm sorry. If you don't, I'm sorry, because it's also sometimes a little bit complicated. The main reason for this is not to tell you how the method works, but more to tell you some of the issues that we have to tackle, some of the challenges. And then a little bit about how we do the analysis, how we do our sampling, and then on to our case studies at the end on firstly the silver dirhams and lastly the lead seals. And I've just added a slide on gold, something else which we can discuss, which is a nice follow-up from Marco's presentation. So this is one of those galleries, if you like, a mining gallery. This is a much earlier, an antique one in Greece, and essentially most of the silver that was being produced doesn't actually come from silver ores, it comes from lead, and argentiferous lead, literally meaning lead that bears silver. Lead that contains silver that's worth extracting. Not all lead has a lot of silver, and some lead has a lot of silver. And so the threshold for what considered to be argentiferous lead is debated, but the Romans were extracting silver from as little as 150 parts per million in the lead. So if you imagine you're melting down tons of this stuff just to get kilos. And what we're doing with lead isotope analyses is trying to figure out where metals come from. And the technique is essentially based on lead isotopes, which you find in lead metal. Thankfully, lead is in a lot of metals. And in a lot of ore deposits, and so what we're looking at is the ratio of different isotopes of lead, and in a nutshell, thorium and uranium part of the Earth's continental crust, and they decay, and the rate at which they decay gives us varying amounts of these isotopes. Lead-204, the little one on the left, that's primordial, that always exists, but the other ones essentially come into being as the uranium and thorium decays. And so essentially what we're looking at is the age, the geological age of something. The older it is, the more the uranium and thorium has turned into lead. The younger it is, not so much. So with isotope analysis, we are really talking about geological ages when things were formed, and then we want to try and match metals from those deposits that have the same isotopes. And that's just a graphic to show you the decay of uranium and thorium. So that's out the way. Now, so with lead metal, you can extract lead from lead oxide, but also galena is the ore, the lead ore, which is a lead sulfide, and thankfully with that you just heat it up. The sulfur comes off and reacts with the air to make sulfur dioxide gas, and you're left with a clean lead metal. Now once you have that clean lead metal, somewhere in there is a little bit of silver. And that's where you want to try and take the silver out. And when you do this process on a very large scale in the Roman period, also down to the very minute scale for those who are testing ores, alchemists, whatever, they want to see roughly how much silver is in. Essentially, you melt the lead in an alkali-rich environment, something rich in calcium, you know, with maybe a lime-rich clay with lots of shell, or you might have crushed bone, ash, and the lead reacts with that to form lead carbonate. And so the lead reacts away, the silver is quite happy on its own, doesn't want to react with anything, so you're left with this small puddle of silver. I've just taken these pictures from a paper published by Maxime, which I think shows nicely how that works. The lead goes into this matrix, and then you're left with your silver pool. And in this case, tiny little beads, which he was experimenting on, which is what you would see in some workshops where they're testing the quality of ores. They want to literally see how much silver is in this lead. You do get silver from other sources, primary silver, native silver, but these are, by comparison to argentiferous lead, these are minute and very early on. Now, thankfully, since the 70s, their Stoss scales, Sophia and Noel Gale, Sophia Stoss scale, they've been working on isotopes from all around the Mediterranean, you know, starting in Lavrion, and there's a huge amount of published data. Since then, more data is being reanalyzed and reevaluated for better precision with new instruments. There's new things being added, and there is a real concerted effort to get everything accessible for everyone to use, and that's this global Lead ID project led by Sabine Klein in Bochum. So this is nice to use. There are other data sets to use. So we have a large reference data to draw on from all over the world, especially in the Mediterranean. We're sort of looking at Mediterranean and Europe, points of interest for us, something in the order of 7,000 to 8,000 raw data points. And Alex's hypothesis makes it really nice for us to try and answer a simple question. Does it come from Sardinia? Does the silver come from Sardinia? And that's nice, because that's not tell me where it comes from, but doing some hypothesis testing is nice. And what we essentially do is we'll take our result from a coin or an artifact. Here is represented right in the middle of this plot, and then essentially see which are the closest points to it, or the closest Euclidean neighbours. Now this gets complicated if you put all the data on at once. You can say, oh, that could be Iran or that could be Argentina. But we have to put our context and logical hats on and say what is a realistic source and what is not. So that's where things like archaeological context, history of mining, primary evidence for mining comes in. And you shouldn't compare 19th century mines with early medieval silver. But you might want to think about those mining areas if there might be evidence for mining in the past. One point in particular for Viking silver, for example, is there's mining in the Harz Mountains in Germany, which was dated to around the 11th century. It's a bit too late for the silver that they're interested in. However, very, very recently, a new publication came out on mining evidence in the Harz Mountains with primary dating that now takes it back to the 9th century. So this is a significant development, because now we can really consider this as a source for that period. Some of these issues, essentially, when you get plots of lots of points, people can overlap them, hide things, show things, and it really depends how you choose to show your data, you can manipulate it quite significantly. One of the things I was pushing towards was having everything transparent, essentially, so you can show everything on the same plane. Nothing gets over plotted, and also looking at probabilities rather than actual points themselves, because they don't exist as a static point, but they're a point within an error, within a cloud of error, so they could be anywhere in that space, and the error in many of these is smaller than the symbols themselves. And here, quite nicely, when you get fields that separate geologically and isotopically, then when you hit one, it's very nice, but it's not always that simple. One of the things that is up for discussion in the literature and has been something we've been aware of is this issue of mixing metals. Sometimes it's very straightforward. So this is earlier work. You can see this very linear line of points. And if we're looking at a specific coin series where you've got 4 or 5 of the same coin series, and you plot them, you think, they should be from the same source. But actually, in this case, you get isotopes on a line, which indicates the silver that was used to mint those coins is actually a mix of silver from 2 places or 2 end members. So when it's on a line, that's fine. We've got 2 sources for mixing. But then that goes further when you're looking at more than 1 source, 2 sources. When you get into the realm of, much later on, provenancing seems to work nicely the earlier you are in time. But when you get into mixing periods, it can be more tricky, but we should not assume that mining did not continue taking place on a large scale. It did. Even during the medieval period, reopening of mines and new mining sites from the caliphate in around the Sinai and either side of the Jordan, there's a lot going on. So this is just, you can't see this very faint line. Can you make that out? That was more just to kind of show, in this case, you've got a line connecting points to show there's this mixing cloud or bubble, so to speak. And this will become relevant later because those little crosses at the top are actually dirhams, and they might be having an influence on silver in the north. This is us recently doing some silver mixing. Rasmus decided to volunteer himself for taking these risks. I did the filming. But we're mixing silver, analysing it before and after, because there's a lot of theoretical models on mixing. I'm very much an empiricist. I want to check that physically. So this is something that's come out of Alex's project as well. And we will actually be doing, this is a practice run. We still need to do mixing of actual dirhams that we have permission to do. And that's silver that's melted in a crucible from other silvers. So it will be really interesting to follow this up as a methodological consideration. Yes, there's been a lot of work on silver in the last years. I was very fortunate to be part of Fleur's project at the top in Frankfurt, but since then there has been huge grants from the EU to Roman silver especially, but also to medieval silver. And we're looking, Alex's project is not all on silver, but we have had a substantial investment in that research. And this is, we're looking at 8 or 9 million euros. If you take Alex's project away, the rest are specifically on silver and silver only. So it has been very popular subject, and I think timely with modern discussions of currencies and economy. Sampling. Why do we need to go into the coin? this is to demonstrate why with some silver coins or silver copper alloys, the surface itself can be different from the core for a number of reasons, from corrosion, conservation, intentional alteration. So in the case of having a silver copper alloy, you can dip it in an acid, and what that will do is the acid will react with the copper, take that away, leach it out, and then you're left with this beautiful, very shiny looking coin which has the appearance of being pure silver. And these can go very deep, these layers. So up above they can be up to, well, as you can see here, 0.5 millimeter. So when you're doing, I say this because it's something in our community that we discuss, but when you advertise doing non-destructive analyses with lasers on the surface, it sounds fantastic. But if you can't penetrate into the core, what is it you're actually sampling? What is it that you're representing? So we do try and go, and this isn't always a problem, but if you know it's an issue, you have to get around it. So what we do is micro drilling. You can see here, that's actually a copper coin with a artificial silver surface attached. It's an old, original counterfeit, so to speak. But as opposed to lasering, we will drill into the coin using tiny bits. I have a coin with me. I'm happy to share. Marco's seen it before, but this is our ideal method where we can discard a little bit of the surface. That can be saved for conservators, but then we can retrieve clean metal from the core. And this is drilling a coin. This is a bronze one. And we collect these turnings, these drillings. That's what we would analyze for isotopes to see where the metal may come from, and also for the metal composition to see how fine it is, to see if there's any characteristics that help us identify mixing or where it comes from. And we go down to less than 0.5 millimeter. Some people do even less. So we target different places. Now the problem with dirhams is they're extremely thin. They're actually too thin for us to drill, and so we opted for taking physical samples. Also because many of these are, as Alex pointed out, they're in their millions. So yeah, having some destructive analyses is something that one can do. And another thing that we're doing at the moment, which is just for future reference, this is where gold can stay where it belongs, but we can come with little quartz rods to make a rubbing on the surface of the coin, and then this gets taken back to the lab in a clean sealed vial for the same analyses. So essentially, in the worst case scenario, we can do something like this where things stay in the museums. So what we do first is we want to know, what is it made out of? Yes, it's silver, but how much silver, and what other elements are there of interest? This is a section of one of those coins at the edge, and you can see here different chemical maps for the different elements. And you can also merge these together to make a false color overlay, and it helps us then to try and take analyses from, as you can see, the core, which is more representative of the metal, and avoid the surface. We still want to check the surface, but that's not representative of the original metal. And as has come up, so that gives us the main composition. And then what we've been doing, though have not been doing more recently, is trace element analyses on the coins using a laser. And a setup with a ICP-MS, inductively coupled plasma mass spectrometry. That's to get the trace elements, those elements that are less than 1,000 parts per million. You know, in many cases, 2 parts per million, 5 parts per million. They can be incredibly informative, especially platinum group elements. Now, the thing is, this laser runs on inert gases, one of which is neon, and the biggest producer of neon gas up until the war started in Ukraine was at Mariupol Steelworks. that no longer. So we're adapting. We're actually going back to old school methods, but with minimal quantities of invasion. And once we've done the measurements in a clean lab, these are certified metal-free clean labs, so there's no contamination. These aren't everywhere. There's only, it's a very clean environment where you don't need to worry about things getting messed up, contaminated. So this brings us now to our case studies. The first one is on these North African dirhams. And this is a map showing the distribution of dirhams done by Chris Kilger. And you can see that this takes us way up into Middle, North and Eastern Europe and into Russia. And a lot of this silver is coming from the Islamic world, from mints in Baghdad and from mints in North Africa. So this is a really interesting topic beyond the Mediterranean. And the image here that Alex showed is essentially a more, it's a display of these networks that was done recently by Mahir Hinic, looking at the distribution of dirhams and trying to find these routes going from the Arab world and up north. And this is where the question comes in. Where is the silver coming from to mint these dirhams for Al-Abbasiyya, for Ifriqiya? And so it's a very valid question. Could the silver come from Sardinia? It's famous for its minings, especially in Iglesiente. There's been a lot of work and analyses. There is silver. So this is our question, and this is related to Alex's work previously, is that we've got the historical references to these raids, but as part of the project, connectivity, disconnectivity is what is the actual physical evidence for this? Is there much in the way that survives to indicate these, happened in sources that have been exaggerated? Only presenting some of the results here, but we're now up to over 50 dirhams. The ones we'll be showing mostly are from Ifriqiya, and we also had a few from Cordoba as well out of interest. Now, what we find is these are high purity silver coins, something like 95% silver, and then your usual other bits. They normally add a bit of copper. Up until about 10% copper, you don't really see much of a colour change, which is helpful if you want to make your money go further. So if you have 100% silver, 10 coins, that's that. But if we add some copper, 5 or 10% copper, then our 10 coins can become 11 coins, so to speak, and not much noticeable difference. Now, the copper being added, you can see in the bottom left, it's copper and tin. Essentially, the copper is clean, but we do have a couple of indications to show that the copper being added was actually, I don't want to say dirty copper, but copper that had been previously alloyed. So in this case, bronze, or even just a copper alloy, which had been bronze at one point. This is important for us to understand, because when we're doing our isotope analyses, we are looking at the lead. We're not actually tracing the silver, we're tracing where the lead comes from. So we're always isolating the lead part to get the isotopes. So if the lead has been added, then that's very interesting, but we're still provenancing where the lead comes from. So if the lead is native to the silver from the process of cupellation, then we're in a safe zone for seeing where the silver comes from. The lead is a proxy. But if the lead has been added, then we're only looking at the lead. Gold and bismuth are things people have been interested in for trying to distinguish some mining zones. I'm not that interested in it because I don't think it's that clear. So from the chemical composition, the aglabid coins that we've been looking at from North Africa, dirhams rather, they seem to be quite consistent in themselves for gold bismuth ratios, so those two. When the gold content is much, much higher, people are thinking, it's this other district. Here what I've done, and I really hope we can flesh this out with the new analyses, is try to plot the fineness against chronology, against date, against the calendar year, Hijri or Gregorian. But essentially, when you can build that chronology of silver fineness, then you get into the topic of relating it to historical events. And that's what we were able to do in the Rome and Greece project. It matches beautifully with the Second Punic Wars, change in silver sources and what have you. So this is in progress, but it will be nice to see how that ends up. One of the things that Stephen said to me at a meeting in Liverpool 2 years ago was, Tom, do you find any mercury? And I said, no, we don't. But I haven't actually really checked, Stephen. And the peak that we had in the spectra was so small, I hadn't taken it seriously. So we went back to Aarhus, re-looked at the spectra and the chemical data, and lo and behold, half of them were covered. And I don't mean full of mercury, but they had traces of mercury at the surface. And you can actually see videos on YouTube of people doing what I think is quite an ancient practice, which is to clean silver with mercury. Just like you do with gold, you know, it takes out impurities, it gives it a very nice shine and appeal. So, you know, take your dirhams, put them in a mercury wash, pull them out, and they're all shiny. So this is another way of doing it, but there's been traces of that left behind. Also, nice to know technologically, also it's good for us to know these things in terms of contamination, other processes. So we still are safe with our lead. So these are the results, and you think, and this is intentional. This is to show everything at once, which is why it's a bit of a cluster mess. And we have to disentangle it and take it apart. If we look at the age of our samples, and this is the modelled age, what we see is we have one group where the age is quite young, you know, between about 100 million years ago, but then we have another group which is getting up to the 300 range, and these divide very, very neatly between the African dirhams and the ones we analysed from Cordoba. So the yellow is, the ones we're not as interested in, but they're there for the sake of illustration and for interest, but it's the red ones that we're asking the question about from North Africa. These are plotted against Stephen Merkel's data from his previous work, his thesis, and it's just to show we're in the same realm of dirhams. Now, this is the question. Does it come from Sardinian silver? Short answer is no. These blue points here represent the reference data. We've got the references here for ores from Sardinia containing lead, those that are of interest. So these are almost all of them galena, but there are some deposits where there's still lead in them, which could be some copper ores. But essentially, Sardinia is very distinct, and we've got a few points overlapping, but generally speaking, the red is nowhere near the Sardinian silver. So that's our question answered for the hypothesis. So now we go on to thinking, okay, if they don't come from Sardinia, if the silver is not from Iglesiente, where is it coming from? So then we ask, okay, what about those mines in Spain? Well, yes, that is a consideration for the Umayyad coins from Al-Andalus, fine, but even still, our red ones aren't really on the mark. And so we then try, okay, what about yeah, these are the different geological zones for Spain. We'll skip that. But what about Morocco? And this is the paper Alex was referring to that was published quite recently, actually. They've been looking at slags and remains of silver from mining. And yeah, there's clear evidence for mining and silver production at this time in the West. But it's not the source of our silver for Ifriqiya. So we're ruling them out, and now we need to try and rule them in. And that comes up really nicely, potentially, well, unsurprisingly, from the ores that have been analysed from Tunisia, from the same area. So essentially the silver for the dirhams being produced at the Ifriqiyan Mint are being produced from silver in the same region. And that's a nice result for us as well. There are some of these points at the bottom which are maybe a little bit outlierish, which we do need to investigate more specifically. But if we go to the raw bulk source, then we're looking at silver from the area from Atlas Mountains and what have you. And this is just to show our dirhams in relation to some other lead artifacts from the same area. And what's really surprising is two of those from Carthage are right smack bang on the two from Cordoba, so it's making my head a little bit fried. But the rest of the artifacts made in Tunisia are in agreement with our dirhams. This is where the zones are divided up for the Tunisian ores. So these are divided up by, you can see in the bottom left, the Napa zone, the Graben zone, the Diapa zone, and essentially we can see that we've got good alignment with the Graben zone, the red, we've got a nice line there, but we also have with the blue, and these are close to each other, they're close to where the settlement is. So yeah, we've got, so this now makes sense when you break it down, but you have to break it down. And so I wouldn't just shove this in a publication, but it's just to show. So that was our silver dirham results for the first 27 dirhams. Some other dirhams we'll be looking from the Aghlabids are a lot more challenging to interpret. They're a lot more diffuse and spread out. This is a very nice story because it's quite clean cut. But there's something else going on in terms of silver movement in the Islamic world. And this has big implications for silver in the north. Everyone talks about North African dirhams, where they're coming from. They're being, maybe not very good quality. They're, being dumped in other places. I don't think that's entirely correct, but silver is also being used to mint the first coinages up in Scandinavia and also in Northern Europe. So where this silver comes from in relation to those long scale networks is really interesting. And this is another project we're working on at the same time. And this is to bring it back to that idea of mixing. If you have local silver from previous coinages being mixed with an influx of silver from elsewhere, like the millions of dirhams that are found on Bornholm, then this might explain why we have some of this clustering without linearity. These are our newest results. Again, provenancing lead using lead isotopes, which sounds straightforward. And my hypothesis was this is easy because lead's abundant, lead's everywhere. You get some old lead pipe or lead sheet and it should be homogeneous in terms of its signal. We're actually entering a discussion on lead mixing now, which I hadn't really anticipated. But then it starts to make you think, if there is lead mixing, why is there? And I think it's just a very practical thing. If you are getting scrap metal and using it in large quantities, no problem. But if you are a scribe who's about to attach a seal to a document, where do you get that lead from? Is it just in that pile of seals that you've just received and you want to reuse or upcycle? Do you carry some pre-weighted forms with you in a bag, or do you just pick up any small? We're not talking about vast quantities, and in some ways it's easier just to grab that bit of lead that no one's using than to be carrying kilos and kilos of it. What you can see here on the left is a rubbing. So where it's a little bit shiny, we do two, one to take away the corrosion. We still save that. And then the other one is to get fresh metal from the actual lead itself. Same question. We have the historical evidence for these visitations or incursions. And these lead seals, as Alex was describing to me, can be on money bags, can be on consignments, so there's different forms. Could any of this be from lead taken from Sardinia? What we found from the chemical results is I think we're hitting I don't want to say needle in a haystack, but we're only just starting this, and this will be really nice to go further with Byzantine seals as well. But two of them have a huge amount of tin, so I would call that pewter, which I was not expecting. I consider that to be something later and somewhere else. But otherwise, the rest of them are essentially pure lead, and there's not much else to say than pure lead, and some of them can be grouped a bit more together based on their composition. Those that have the bismuth in, and the two I've highlighted here not very clearly is 14A and 10. They're very similar in their composition, and they're those two seals shown there, and they're the special ones because what we found with those two seals is their geological age is really old. They're bang on 619 million years ago, and those ages fit exactly with Iglesiente. I'll show you. So these are our seals in a nutshell, and we're looking at Mediterranean sources or mixtures thereof, mainly Spain, Greece, Turkey, same geological kind of belt, and then some candidates which are potentially Sardinian or North African. Two of them specifically, there's 2 points there at the top overlapping each other, 10 and 14A. And it's those two that have provided the cleanest match for Sardinian lead metal. Here there's a list for each, just to show you a bit how it works, of the nearest 25 neighbours. And these Euclidean neighbours are within the error. This is like 1 point amongst a whole load of points in a tiny space. And nearly, all of them are Iglesiente, Southwest Sardinia, gallinas, which have ages of 620 million years ago. So we have two lead seals, at least we can be sure, are Sardinian lead. From my mind, there's no doubt about it. There are no other overlapping sources. There are no other points of contention, and it's clean lead. So in terms of provenance hypotheses, silver is coming from where it's being minted. The lead seals seem to be varied in their sources, but we have a Sardinian connection. And I think that would be interesting with the Byzantine seals in the future to do rubbings and see what's going on there as well. These are the ones that should come out, 2 of them this year, the other 2 hopefully, so be able to read this up soon.